Congratulations for reaching this last lesson. This lesson deals with the dynamics of circular motion. In Unit 1, we have discussed uniform motion and circular path. We learned that, even though the magnitude of linear speed, or tangential speed, does not change, its direction is continuously changing, as the object moves along circular path. This change in direction of velocity corresponds to acceleration, called centripetal acceleration. In order to produce this acceleration, from Newton's second law, a net force must act on the object called centripetal force, denoted by the symbol, summation of F. Centripetal force is the constant inward pull, or net force that deflects a body from its straight path, and compels along a circular path. To explain this, imagine a ball of mass m, that is moving a constant speed v, along a circular path of radius r, by means of a light cord rotated about the axis so. As the ball travels, the centripetal force, summation of F, allows the ball to move on this circular path, thus changing the direction of the speed and producing centripetal acceleration on it. The tension in the cord provides this centripetal force. Remember, without centripetal force, an object cannot move on circular path. It is the force that compels a body from straight-line motion into circular motion. If in case the string breaks, the tension in the cord, which provides the centripetal force, vanishes, and the ball will be thrown, and will no longer move along circular path. From Newton's second law, net centripetal force, summation of F, is equal to the product of the object's mass and its centripetal acceleration. Take note that centripetal force is always directed towards the center of rotation, and it is the net force acting on the object, and therefore, we need also to draw the free body diagram of an object, in order to take into account all the forces acting on it. Alright, let us answer this first problem, which involves dynamics of circular motion in a vertical plane. Problem number 11. A Ferris wheel with a radius 14 meters, is turning about a horizontal axis through its center. The linear speed of a passenger on the rim is constant and equal to 8 meters per second. If the mass of the passenger is 50 kilograms, letter A, what is the centripetal force acting on the passenger? Letter B, what is the apparent weight of the passenger at indicated points A and B? Now, let us list down all given information. The radius of Ferris wheel is 14 meters. The linear speed of the passenger v, is 8 meters per second. And the mass of the passenger is 50 kilograms. We need to determine the centripetal force on the passenger, and the apparent weight of the passenger, which is equivalent to the normal force. So let us analyze the problem. The Ferris wheel is rotating on a vertical plane. We know already that a centripetal force must act in order for the passenger move on this circular path, and it is always towards the center of rotation. If the passenger is located at point A, that is on the highest point, the centripetal force is downward. If the passenger is located at point B, that is on the lowest point, the centripetal force is upward. We see here that regardless of the position of the passenger, the centripetal force is always towards the center of rotation. Now let us solve for centripetal force. We need to solve first for centripetal acceleration. From Unit 1, centripetal acceleration is equal to v squared over the radius r. Substituting the values. The speed, 8 squared, divided by the radius 14. So the centripetal acceleration is 4.57 meters per second squared. Then using Newton's second law, centripetal force is equal to the mass of the passenger multiplied by the centripetal acceleration. So 50 times 4.57, the centripetal force acting on the passenger is 228.5 newtons. For letter B, the apparent weight. We have learned from the concept of inertia, that when your body travels on a curved path, the body seems to be pushed away from the center of the turn or opposite to the direction of the turn. As you turn to the right, you feel that your body is being pushed to the left. This effect is also valid in the passenger riding this Ferris wheel. He can feel different sensations, especially when he is at the highest and lowest position of the ride, He feels that something has changed regarding his weight. Sometimes he feels heavier and sometimes lighter. This is actually the excitement you feel when you are riding any carnival ride. And the feeling of seemingly change in weight is called apparent weight. And it is equivalent to the normal force acting on the passenger. Now, let us first solve the apparent weight of the passenger when he is at point A. To do this, we need to draw the free body diagram of the passenger when he is located at point A. So this is our axis. And this is the passenger. In constructing free body diagram which involves dynamics of circular motion, different approaches applied, just like we did in pulley problems. It is important to remember that in circular motion, the center of rotation is treated as positive axis, or the direction of the centripetal acceleration, which is always towards the center of rotation, is treated as the positive axis. So if the passenger is at point A, the center of rotation is located below the passenger, and the direction of centripetal acceleration is downward. Therefore the positive y-axis is directed downward, and the negative y-axis is upward. Then we indicated the forces acting on the passenger. So we have the vertical downward weight, and the normal force exerted by the seat on the passenger. Then we take the summation of forces along y-axis. So we have weight, minus the normal force. Take note that the weight is positive because it is towards the positive y-axis. While this is minus, since the normal force is towards the negative y-axis. We know already this summation of F. In fact, this is our centripetal force from letter A. Solving force normal force, you transpose negative of the normal force, and the centripetal force. So normal force is equal to weight minus centripetal force. But weight is mass times gravitational acceleration. So 50 times 9.8 minus 228.5. The weight is 490 newtons minus 228.5. So the normal force at point A, or the apparent weight of the passenger at point A, is 261.5 newtons. We see that this apparent weight of the passenger, 261.5 newtons, is less than his actual weight, 490 newtons. It means that when the passenger reaches the highest point, the passenger feels a different sensation. He feels lighter than his normal weight because his body tends to move upward or float, or move away from the center of rotation. Now, for the apparent weight of the passenger, as he reached the lowest position at point B. Let us draw the free body diagram. So this is the y-axis. When the passenger is located at point B, the acceleration is towards the center, therefore it is upward. Hence, the positive y-axis is also upward. And the negative y-axis is downward. Again, the forces acting on the passenger are downward weight, and the upward normal force exerted by the seat. Then we take the summation of forces along y-axis. So we have normal force minus weight. Take note that the normal force is positive because it is towards the positive y-axis, while this is minus, since the weight is towards the negative y-axis. Then we solve for normal force by transposing weight to the other side. So normal force at point B is centripetal force plus weight. Centripetal force is 228.5 plus weight, mg, which is 50 times 9.8. So the normal force, or the apparent weight of the passenger when he is located at the lowest position is 718.5 newtons. Here we see that the apparent weight of 718.5 newtons is greater than his actual weight of 490 newtons. The passenger feels heavier than his normal weight, because his body tends to move downward, thus, producing greater pressing force on the passenger seat. That's it. We see that, based on our computation, when you are located at the highest point, you seems to feel lighter, while at the lowest point, you seems to feel heavier. How about as you are located at either of the side? What is your apparent weight? What will be the reaction of your body, or what sensation do you feel? I leave that for you to think about. Okay class. This time, is your turn. In previous problem, we consider circular motion in vertical plane. Now let us see what you have learned by answering this problem, which involves circular motion in a horizontal plane. Exercise number 6. A small plastic box, with a mass 0.3 kg, revolves uniformly in a circle on a horizontal frictionless surface such as air hockey table. The box is attached by a cord, 0.14 meters long, to a pin, set in the surface. If the box makes 2 complete revolutions per second, find the force exerted on it by the cord. In problem number 11, we investigated the dynamics of a Ferris wheel, which is revolving in a vertical plane. In this sample problem, we will investigate a car, which is rounding a flat horizontal plane. Problem number 12. A 800 kg car is rounding a flat, unbanked curve with radius 20 meters. If the coefficient of static friction between tires and road is 0.6, what is the maximum speed at which the driver can take the curve without sliding? So let us analyze the problem. As seen from top, this is the car, of mass 800 kilograms, which will make a turn on this unbanked curve, of radius 20 meters. The coefficient of static friction between tires and road is 0.6. Now, we are asked to solve for the maximum speed, v, at which the car can negotiate the curve without sliding. To negotiate the curve, centripetal force should act on the car as it moves. But the question is, what will be the source of this centripetal force? How this force will be provided on car? Now, let us draw the free body diagram of the car. We consider the rear view of the car. So this is the unbanked road. Unbanked road means that the road is horizontal. We put here our axis. This is the center of the curve. Take note that the center of the curve is considered as positive axis. So this will be positive x-axis. And this one will be negative x-axis. For y-axis, we use only the conventional. Then we try to indicate the forces acting on the car. So we have downward weight, upward normal force on 4 wheels of the car. Now, as the car negotiate the curve, the car tends to move out of the curve or tends to move away from the center of the curve. To prevent this, the road will exert static friction on the wheels. The direction of this friction is towards the center of the curve. In fact, this is the centripetal force acting on the car. The friction serves as centripetal force enable for the car negotiate the curve without skidding out of the road. If the actual friction is already at maximum value, it means that the car is also traveling at maximum speed, wherein they can still take the curve safely. Now, let's begin the solution. We are to solve the maximum speed. We will begin with the formula of centripetal acceleration. Centripetal acceleration is equals v squared over radius, r. This centripetal acceleration is towards the center. Solving for the speed, v equals the square root of centripetal acceleration times radius. Then, for the meantime, we label this as equation 1. We do not have the value of centripetal acceleration, so we cannot solve immediately the speed v. Let us check what we can do to solve for centripetal acceleration. Now, from Newton's second law, the summation of forces along x-axis is equal to mass times centripetal acceleration. From FBD, we have only one force on x-axis, the maximum static friction, Fs max. So this is equal to mass times acceleration. But we know that static friction is also mu sub s times the normal force. From here, let us see if we can solve for centripetal acceleration. We know mu s, but we do not have the value of normal force, therefore we cannot solve yet the centripetal acceleration using this equation. So again, for the meantime, let us label this as equation 2. Our problem here is the normal force. Now let us consider the summation of forces along y-axis to be 0, since there is no motion along y-axis. From FBD, The forces along y-axis are normal force minus weight, so this is equal to 0. But weight is mass times g. Then we transpose, therefore normal force is m times g. Although we have the value of mass which is 800 kilograms, but we rather not solve the value of normal force, instead we substitute this to equation 2. Hence, equation 2 becomes, mu sub s, times m times g, equals, m times a sub c. So we can cancel out mass m, so it means that the solution is independent on the mass of the car. So the centripetal acceleration is equal to the product of the coefficient of static friction and gravitational acceleration. Then lastly, we substitute this to equation 1. So equation 1 becomes, v equals the square root of mu sub s gr. Now this is the final equation for the maximum speed, for which the car can safely turn on this unbanked road. As you can see, the maximum speed is only a function of coefficient of static friction, gravitational acceleration and radius of the curve. It is not dependent on the car's mass. Substituting the values, so the maximum speed will be 10.84 meters per second, or approximately 39 kilometers per hour. In other words, this is the limiting speed. If the car travels above this value, the car will skid out of the road, which will lead to serious accident. So please slow down before negotiating a curve road. In public works and highways, signboards are installed to remind on the limiting speed as safety measure. Just to be more safe, the value in signboard should be lower than 39 kph, let's say, 30 kph. This last problem is related to previously solved problem. Problem number 13. During rainy season, the road in previous problem becomes virtually frictionless. It is necessary to bunk the curve at just right angle, so that no friction at all is needed. Using the data in previous problem, at what angle, beta, should the curve be banked so that the car can make the turn safely even if there is no friction? In previous problem, if there is no friction, the car cannot negotiate the unbanked curve road, no matter how slow the car moves. So engineers found that one of the solutions is to bank the road at a certain angle. This angle is called banking angle. First we draw a free body diagram of the car. So this is the road and the car. This is the x and y axis. We make some projection to see the center of the curve. This is the radius of the curve, 20 meters. Then we indicate the forces acting on the car. We have downward weight and the perpendicular normal force. We resolve weight in terms of x and y components, w sub x and w sub y. The angle between w sub y and the weight is also equal to the banking angle. So this is also beta. And the angle between the radius and w sub x is also beta. We label also the centripetal acceleration of the car, that is, always towards the center of rotation. Now, that we have fully analyzed the problem, let us begin the solution. Since the acceleration is towards the center, or that is along positive x-axis, so we can use Newton's second law. The summation of forces along x-axis is equal to mass times the centripetal acceleration. And from free body diagram, there is only one force acting along x-axis, that is w sub x. In fact, this x component of the weight serves as the centripetal force acting on the car. So in absence of friction, w sub x compels the car to move along the curve road. So w sub x is equal to mass times centripetal acceleration. But w sub x is also w sine of beta. And the centripetal acceleration is v squared over r prime. And this is r prime. Take note, we did not use the 20-meter radius, instead we will use the effective radius r prime, since the radius and centripetal acceleration must be parallel to each other. That's why we use r prime instead of the given radius, 20 meters. But weight is also m times g. So we have m, g sine of beta equals, mv squared, and a little knowledge of trigonometry, As you can see, this is a right triangle, so r prime is also equal to the radius r over the cosine of beta. We further simplify, we can cancel out mass. Again, this proves that the solution is independent on the mass of the car. So the equation becomes g sine of beta is equal to v squared cosine of beta divided by r. Then we cross multiply cosine of beta, as well as the gravitational acceleration to other sides of the equation, so it becomes sine of beta divided by cosine of beta equals v squared all over gr. Can you recall this form of trigonometric identity? The ratio of the sine and cosine of an angle is also tangent of that angle. So this expression becomes tangent of beta. Lastly, we solve for beta. Beta is equal to the inverse tangent of v squared all over gr. Substituting the given information. So the banking angle needed is 31 degrees. So even if there is no friction, the car can turn safely on this curved road at a maximum speed of 10.84 meters per second. And here's another idea. What will happen to the car if its speed becomes greater or lower than 10.84 meters per second? Try to think of it. And if you know the answer, notify me. I will give you plus points. Is that okay? Wow! And that concludes our discussion in Unit 2. Congratulations! And thank you for staying with me up to this point. And try not to forget all of the stuffs we learned from this unit, because this is just the beginning. See you later.